Hello all. So today we're going to look at the concept of complex power, and by the end of the session you should be able to derive the instantaneous power in an AC circuit, sketch graphs of instantaneous power in R, L and C components, explain the terms real, apparent and reactive power, compute power in the phasor domain, draw and explain a power triangle and explain the terms lead and lag. This is a very important session, and we are going to cover some very tricky concepts. So if you need to look at uh, the video over a few times, please do that, because these concepts are really critical to the work we're going to do. So we're going to start now with two variables, v and I, and v cosine omega t plus angle theta v, and I cosine omega t plus angle theta I. If I would like to find the instantaneous power, I simply multiply these two together point by point, and I will get vi cosine omega t plus theta v multiplied by cosine omega t plus theta I. I could simplify this, and I will end up with two terms, one a constant term and one an oscillating term. So even though I have two sine waves, V and I, when I multiply them together, I get a single sine wave with some offset. So this is the offset, which is the constant, and the oscillating part of the term. So unlike multiplying current by impedance, remember impedance is not a sine wave, impedance was just a complex number, so it was a constant. So when I multiply a sine wave by a constant, I get another sine wave. When I multiply two sine waves together, I get a sine wave with an offset. So that is a very important thing to remember. So I'm going to look now at the power through a resistor, and we know for a resistor the voltage and current are in phase, so theta v minus theta I will be 0. So if we look back up here, I've just put the final equation from the previous slide, and theta v minus theta I is 0, cosine will go to 1. So here I will have now vi on 2 plus vi cosine 2 omega t plus theta v plus theta I on 2. So we have the double of the frequency of the voltage and current. So we cannot talk about power being in phase or out of phase with voltage and current, because they are two separate frequencies. The power is at twice the frequency of the voltage and current, and also we have an offset. So this is for a resistor. If I go to a reactance, when theta v minus theta I is 90 degrees or minus 90 degrees, then what I'm going to have is that cosine theta v minus theta I, I'm going to get cosine of 90 or cosine of minus 90, which is 0, and all I'm left with will be this part here, which is the oscillating part. So for a reactive component, that is a capacitor or an inductor, what I'm going to see is that the power oscillates. So if I look back at the resistor, notice that the power for the resistor, well, here it goes a little bit below 0, but it really should not go below 0. It should stop at 0 and go back up. So the power for the resistor is totally positive. It is offset by the amplitude. So you can see here, this is the amplitude of the cosine wave, which is the same as the offset, so that it never goes below 0. It is unipolar. For the reactive components, we have a sine wave, a perfect sine wave. So we have equal parts above and below the 0 line. And what this corresponds to is the expansion and collapsing of the field. So if we have a capacitor, we have an electric field. So when it is the electric field is being charged, we have positive power entering the field, and then when it is discharging, we have the power being released back into the circuit. And same thing for an inductor. If we have an inductor, as the magnetic field is expanding, it means energy is going into that field, and when it starts to collapse, the energy is released once more into the circuit. So the average power dissipated by a reactor, that is a capacitor or an inductor, is zero. So it doesn't actually use power, it simply shifts the power in the system. So the reactive power just circulates in the system. It never actually gets dissipated. So, and this corresponds basically to the energy that is stored in the fields of the capacitors and inductors. So, now let's look at the concept of average power or real power. So if we look at our total equation, the average power, real power, this is the power that is actually dissipated, is this constant term in front here. And we saw that that disappeared for reactive components and it remained for resistive components. So this is the part of the resistive component. This is the component of the resistive power which is dissipated as heat. So, well, the average, this is the average value that is dissipated as heat. So if I look at that value, I will see that I could just convert this form into V on square root 2 by I on square root 2 cosine V minus theta V minus theta I. So V on square root 2 is the same as VRMS, and I on square root 2 is IRMS. So I can represent that on a diagram. If I had V and I, it means then that this average power, which is VRMS, IRMS, cosine theta V minus theta I, is the product of the voltage and the projection of the current onto the voltage direction. Now, here you'll see why, if I go back up, here you'll see why we chose to use the RMS voltage as the magnitude of the phasor as opposed to the amplitude of the voltage as the magnitude of the phasor. So here, if I have VRMS multiplied by IRMS, I would get this directly from the product of my phasors, and we'll see that in a little while. So I have this product between the voltage and the projection of the current onto the voltage, which is cosine theta V minus theta I, and that gives me my real power. And if I take the product between the voltage and the perpendicular, the projection onto the perpendicular to the voltage, that would give me what I call the quadrature voltage, or the quadrature power, the reactive power. So this corresponds to the power that is stored in the fields of the capacitors and inductors and so on. So the complex power, we looked at what is real power and what is reactive power. The complex power is simply the complex sum of the real power and the reactive power. So we just can't add them to each other. So we use P as the reference with zero angle, and then Q is on the imaginary. So it is P plus JQ. And if I write that out, I'll get VRMS, IRMS, cosine theta V minus theta I plus J sine theta V minus theta I. I can now take Euler's identity and convert that into this form, which is my phasor form. And I will see that that corresponds directly to V multiplied by I conjugate. Now we know from our DC circuit analysis, if I had to find the power and I had V and I, then I would say P is equal to VI. So P is equal to VI. This is real power is V multiplied by I. Here I have complex power, S is equal to V multiplied by I conjugate. If I take this down to zero frequency, so I take it to a DC circuit where the frequency is zero, it means that there will be no phase shift at any point in the circuit. So the current I, which is equal to some A plus JB, if I look at this as a DC, there will be no B component. So I is equal to I conjugate. Remember, if I is equal to A plus JB, then I conjugate is equal to A minus JB. But if B is equal to 0, then I is equal to I conjugate. So for real power alone, for S is equal to P, I is equal to I conjugate, and this reduces to P is equal to VI from S is equal to VI conjugate. So the other thing we should note here is that in these equations we have no time and no frequency. So these are all average values, and the values here are dependent only on the relative separation of the voltage and current. It does not depend on the frequency at all. Of course, it will depend in a sense on the frequency because the reactances in the circuit depend on the frequency, and the larger the reactance, the smaller the current, and so on. So there is some dependency there. But if you look at the angles here, they do not depend on the frequency directly. That is, if we are using this equation, theta v minus theta I, S is equal to VI conjugate here, then that doesn't come into play. So, in summary, we have three types of power: the real power P, the reactive power Q, and the apparent power S. The units for P is watts, the unit of Q is the VAR, this means volt amp reactive, and the unit for S, I don't have it here, is VA, or simply volt amps, because it's directly V multiplied by I, voltage multiplied by current. And if we have a resistive circuit, then we will get the power totally positive with an offset equal to the amplitude of the oscillation. And if we have a reactive component, then the power is a sine wave and, well, a sinusoidal wave, and the average power is 0. So we have an average power, a non-zero average power for resistors, but no average power for reactors, that is capacitors or inductors. And we've seen that S is equal to VI conjugate. This is very, very, very important. Make sure and get this correct. It is a conjugate of the current that is used, so whatever the angle of the current is, you have to make that negative in order to find the apparent power properly. So, just to summarize some more, since we had different things with angles, for a resistor, we have, assuming we have V angle 0, we have the current will be IR angle 0, which is the same as the voltage. For an inductor, the current lags by 90 degrees, and for a capacitor, the current leads by 90 degrees. So if I look at the power associated with the resistor, then when I take VI conjugate, it will be VI angle 0. Since the angle here is 0, then the conjugate will carry the same angle. If I have the inductor, then when I take VI conjugate, I'm going to get VI positive 90 degrees. And when I look at the capacitor, I'm going to get VI negative 90 degrees. So notice the angles for power and current are the opposite. So when we have a combination now of P and Q in the circuit, then we could find the total complex power, the total apparent power directly. And we could do this just like we would do in a DC circuit. So when it is that I have a DC circuit, if I have two resistors, R1, R2, and I will say RT is equal to R1 plus R2, and then I could find I is equal to V on RT and P is equal to VI. I could do the same thing here. I find ZT, the total Z, just like I find the total R. Then I could find I, which is V on Z theta, just like I find I here. Then, just like I find P here, P is equal to VI. Now I could use S is equal to VI conjugate. And that will give me what the apparent power is. And the real part of that is my real power, and the imaginary part is my quadrature or reactive power. So usually what we will do when we do this, when we find the apparent power, is we will break it up into P and Q, and we often represent this on what we call a power triangle. So the power triangle just simply shows us the relation between P, Q, and S. And P is always on the horizontal, and then Q, we usually tag it on to the end here, and it will be either going upward if it is inductive, where we have positive Q, a positive angle. Remember, if we go back here, inductive Q will have a positive angle of 90 degrees, and capacitive Q will have an angle of minus 90 degrees. So if we have QL, inductive Q, we will get the arrow going this way, and this way if it is QC. And the apparent power is simply the hypotenuse of that right angle triangle. So one or a couple of terms that we will typically hear when discussing the power triangle are the terms lead and lag, and these describe the relationship between the real and apparent power. When we talk about lead, we are talking about a negative angle, and lag, we are talking about a positive angle, and that might seem counterintuitive, but really what we're talking about here is the relationship of the real power to the apparent power. So you'll say the real power lags the apparent power by theta degrees. So that is what we're looking at. The real power leads or lags the apparent power. So as we had here, for a positive angle, P lags S. And you'd normally talk about that, you'd hear the term lagging power factor used a lot in the power industry. This is because we have a lot of motor loads, transformers and so on, which are all inductive elements. So we have a lot of energy stored in magnetic fields of the inductors, and that gives us positive Q. So we always have a lagging current, a lagging load. So let's look now at sketching some phasors for power. So if we have a simple RL circuit, I could get the magnitude of the apparent power, S is equal to VI conjugate, which is the same as I squared Z, just like you'd have I squared R in a resistor in a DC circuit. I have the magnitude of I squared here multiplied by the magnitude of Z with an angle of theta Z. So I have that, or I could look at it as the real power is I squared R. This is the RMS current multiplied by R, the magnitude of the RMS current multiplied by R. And the apparent power is the magnitude of I squared multiplied by XL, which would be the inductive reactance. So just like if I had two resistors in a DC circuit and I wanted to find the power, I could find the power dissipated in this one and the power in this one and add them up. I could do the same thing here. In this case, the power dissipated in the resistor is real power, and the power dissipated in the inductor is apparent power. So the power dissipated in R will correspond to P, and the power dissipated in L will correspond to Q. So whether I did it that way or I found the total impedance and then multiplied that I, by the current, I should get the same thing. So in one way, if I combine the impedances, I will get this vector here with this angle, the angle theta z. The other way, if I calculate it for each one of these individually, I have to know that the R corresponds to P and the L corresponds to Q. So hopefully by now you should be able to derive the instantaneous power in an AC circuit. You should be able to sketch the graphs of instantaneous power in R, L, and C, and these are just the graphs that are double the frequency. For R you have the offset, so the power does not go below zero, and for L and C they are sine waves. Both are double the frequency of the voltage and the current. Remember, you cannot represent power and voltage on the same phasor diagram because they are both different frequencies. You should be able to explain the terms real, apparent, and reactive power. You should be able to compute the power in the phasor domain. This is your S is equal to VI conjugate, and that is equal to P plus JQ. You should be able to draw and explain a power triangle and draw a power triangle from a circuit diagram and explain the terms lead and lag. And remember, with lead and lag, you're looking at the real power leads or lags the apparent power.